Thank you all for coming. Welcome to lecture 5 of our course. I hope you're enjoying the course so far. Last lecture I wanted to do, but I couldn't because I had a flu and I couldn't really speak. This week it's much better. I think Tanush did a very good job doing the last lecture. This lecture today will be on computer vision. The lecture itself will be a bit more dry because we have a bit less quizzes, a bit less programming or live programming, but we need to go through some of the basic elements, and then afterwards we have the tutorial where you are able to put all these elements together and actually program yourself. What we do today is talk about computer vision. So first of all, we want to explain a bit what machines see. So what is a digital image? How does it look like? How can we process that? And then we talk about the challenges that are inherent in computer vision problems. So why is it such a difficult problem that is very difficult to address with standard computing or more traditional approaches? And then afterwards we show how these convolutional neural networks have really changed the way of processing images and how they work. And then later in the tutorial you will also see how to apply them yourself. So I explain the concept of features in computer vision. Then I explain the standards of convolutional neural networks, CNN architectures, and that's essentially it. And what we structure in the lecture is basically we start with what is computer vision, so with the standard definition, and that's what we do right away. So what is computer vision? Again, computer vision, the definition has changed a bit over time. Why? Because around 2012, and I think we had that in the history overview in the beginning, there was this big breakthrough with convolutional neural networks, so basically deep learning methods. And during that time also definition of computer vision changed a bit. What we did, we picked a relatively general one, which is essentially computer vision is the process of using computers to extract information or useful information from images. So very general definition, doesn't tell you much about what the method looked like. And if we talk about computer vision, we first need to think a bit about human vision, right? So what do we see? How do we see? And I'm sure you had that in high school at some point a bit. Right? So I don't want to go into detail. I have actually no idea about the details. But in general, I think the concept is clear. We have light entering our eyes, right? That is converted to electrical signals, which are then interpreted by our brain, right? And if you think a bit more technical about human vision, we have two eyes. In that sense, it allows us to have a perception for depth in the room, for example, here, right? And we have a relatively high resolution. So we have a lot of, so there's a very, very strong visual perception we have as a human compared to like cameras that used to be around here that we have in our phones, for example. And having our visual perception, we are able to differentiate a lot of different objects, right? So if I show you these two objects, for you it's very clear that this one is some kind of car and this one is some kind of human, right? But the question is, how can we actually differentiate? Like, what are the features that we see as humans that enable us to say that, hey, this one is driving and this one is a human? And that question goes to you essentially. So can you tell me why is this a human for you, and why is this some kind of car for you? Like, why do you make this decision? Anything that you recognize, anything that you, yeah.
The brain has a very large part of it associated with recognizing faces.
Mm-hmm.
So that's something we're actually really, really good at.
Mm-hmm.
People. So that's why we're able to recognize the face as it is based on structure, and why we sometimes also see faces where there aren't any, for example, clouds.
Yeah.
So that's essentially what the brain does for us.
So you're saying we have also gone through this learning process throughout our entire life,
Evolution, essentially.
collected a lot of experience, which enables us to differentiate those, exactly. So the question is, we can do it, but do we understand precisely what we do, such that we can also put it in the computer program? And that's what basically this lecture is about. Like, how can we understand perception in a way that we can formalize it, put it in a computer, so computers can also make these differentiation. And if we think back to, I think it was lecture 1, where we talked about machine learning. Machine learning, we had this issue of supervised learning, unsupervised learning, where in supervised learning we had regression classification. When we talk about computer vision, many of the problems are classification problems. So in most cases, what we deal with is basically we get an image and we want to differentiate what do we see on the image. That's classical classification problem. And together with the classification, usually comes the data. And classification is supervised learning technique, so usually we have also labeled data. So usually our machine learning algorithms are based on a lot of data, so a lot of image data together with corresponding label. Okay, so before we go into detail of how the machine learning models look like, I want to briefly talk about how an actual image looks like for a computer. And if you think about it, I'm sure everyone is aware that images in computers, so digital images, are based on pixels, right? So if you zoom into digital images, at some point you will see these pixels, right? And each pixel is the smallest unit of a digital image. And if you count them, basically you get the resolution of your image. And then the image formats are usually somehow compressed, so we can process them on the computer. Common formats you're aware of are JPEG, for example. And if you think about color in images, usually the color is encoded in some kind of color space that could be RGB, for example, which basically means that instead of having one matrix representation of an image where we just have for each pixel one value, we usually have 3 representations, each representing one of the color spaces. Okay, so if you think about colorful images in computers, so digital versions, what I would like you to think about is matrices essentially, and large matrices, right? So we're talking about large, high-resolution images to some extent, so we have a lot of matrix values here inside. If we talk about grayscale images, usually we have only one color space, so usually one matrix. And thinking about this, so images as matrices, shows us a bit why it's so difficult to process them. Because first of all, we have very high dimensional input spaces, right? So we're not having this very easy mapping from X to Y, like in regression, right? So we have maybe one input, maybe 10 inputs, to 1, 2, 3 outputs. Now what we have here is we have huge dimensional inputs structured in a matrix that we want to map to one-dimensional output, or maybe 10-dimensional output if we have 10 different categories, right? So the question is, if I give you such a matrix system, can you program a computer program that tells you, hey, that's a distillation column? And this is so difficult because most of our algorithms in machine learning are somehow based on similarity, right? So usually say if something is similar in the input space, so in the X, the output space is also somehow continuous, so it's similar, right? So if you try to learn a function, it's somehow based on this relationship between the inputs and the outputs. However, in computer vision, that is not a bit tricky. So for example, if you have these 2 images here, the output is similar, right? So both of them are cars. Both of them are actually cars with 3 wheels. But if you look at the matrix, at the image, at the values of each individual pixel, they are completely different. So if you compare them one by one, like this pixel with that pixel, well, this one is green and this one is red or so. The images even have different resolutions. They have different aspect ratios, right? So they look completely different for a computer. And that's a challenge, even though for us they somehow look similar. So we need to think about how can we get these information out such that they also look similar for a computer, because otherwise it's not going to work. Otherwise we are trying to solve a problem that is so complex that we will never get there. And there's actually a lot of additional issues. And I will go through these few here with a few examples as well. And all of these make it very difficult for computers to see. First one is viewpoint. So let's say you have some kind of object in a room. If you look at it from different perspectives, if you even make very minor changes, what you end up with is completely different matrices, right? So even if I shift my image for 1 pixel, every pixel entry will be different in the image. Yeah, there's a question. These are representing the. Sorry? What does the 0 to 255 represent?
That's the usual values.
So it's kind of a definition of the color space, I would say. Is that correct? So if you have 255, it's the highest intensity, 0 is the lowest intensity, and it's kind of a definition. So basically, I'm not sure who defined that or what format defined that, honestly, but you could also do 0 to 1 and then scale it accordingly. It's just the maximum and the minimum value they define. Is that clear a bit?
I thought it is something like 8-bit image, so 2 to the power 8.
I'm honestly not sure, and I need to double check. But happy to double check and answer that next lecture. Any other questions? Okay, so we come to this viewpoint again. So this is one of the difficulties here. If you change the viewpoint only a little bit, the image itself looks similar for us as humans. The object itself, it's the same. So the class we want to predict is the same. However, each and every entry of the matrix may be completely different. Likewise, if you change the lighting of your setting, again, the pixel values will be completely different. Even though the object is the same, it's the same class that we want to predict. For us as humans, we're able to differentiate that. For a computer, this lighting changes make it very difficult. There's also a difficulty in interclass variability. So this is something you might know from chemical engineering. If you draw a heat exchanger, and I think last week you drew quite a few different objects, well, we know that this is the way to represent a heat exchanger, and this is just a different way of drawing heat exchangers, right? So there may be situations where we have the same class, but very different ways of drawing them. And same may be true for cars, right? So there's different brands, different colors, different kinds of cars. Everything is a car. And we know that. But for a computer, well, these are completely different things in the first place. So we need to think about how to deal with this challenge as well. And again, if we have this, it will translate to completely different representation in the matrix values. Last one is deformation. Not last one, actually. So if you look at bubble columns, for example, I'm not sure if some of you may have done their bachelor thesis in this, or have maybe looked at microreactors or so. For us as humans, we know that these bubbles may be deformable, but again, for a computer, well, this looks completely different. So the last one, which is not as relevant for core chemical engineering applications, but for many other computer vision problems, well, sometimes it's difficult to differentiate the background from the foreground of an image. And again, this makes it also very difficult for computers to differentiate that and for us to write according programs.